We got a very interesting presentation coming up next. Dr. Mark Everett, I just met him. But Dr. Mark Everett is a faculty member here at TAMU, sorry, I said my Kingsville, Texas A&M University here at Geology and Geophysics Department, specializing in applied geophysics. He's also an author of a textbook called Near Surface Applied Geophysics and is co-editor-in-chief of Journal of Applied Geophysics. Dr. Everett is a state of Texas professional geoscientist. So this is new to me, so I'm going to be very interested in your presentation. Let's give him a hand.
Well, can you hear me okay? So while she's doing this, I'll just say happy to be here, and I'd like to acknowledge the folks at TTI, particularly Tom and Scullion and Darlene Gohl for suggesting this talk I give today. Okay, we're all set. Okay, so my title of my talk is Geophysical ERT Testing at the FM 2429 Bridge. And basically, what we're trying to do is sound out the subsurface with electrical resistivity method. So we have some electrodes that we place into the ground, we measure the voltage, and we put electric current in, and we can image the subsurface for its electrical conductivity and relate that to soil properties, soil moisture, clay content, things like that. So you can see on the right here, we have a system of electrodes that we put in the ground. You make sure that they couple really well, and we can then drive current in. Like you see here, there's some current lines, and we measure voltages, and that tells us a little bit about the subsurface structure. We can use that for geotechnical applications. So this is an example of what a layout would look like. We have the console, we have a regular car battery. Here's our array of 56 electrodes in this case. It takes about about 20 minutes to deploy, depending on the terrain, and it takes about 20 minutes to acquire the data. And you can do this with a crew of 2 or 3 people. And we've done it in quite a few places now in the Texas highways. This diagram shows you that these are your electrodes here. You inject current through 2 electrodes, and you measure the potential through another 2, and you can plot here the voltage. And as you scan across your array, you can then increase the separation between your electrodes and plot them down here. And essentially what you get after you do that is what we would call a pseudo-section of the ground. So it would be sort of a first look at the structure of the subsurface. So for example, here, where we have our current injected here, we're measuring voltage on these electrodes. So we draw these 45-degree lines and plot what looks like the apparent resistivity here. And if it's a low value, for example, we can plot it in one color and a medium in a different color. And if it's a high value, in a red color. And in that way, if we do all the combinations, we can build up a first look at the subsurface. And so we would plot the voltage here across the electrodes and normalize it by the electric current that we put in. And this would be an array factor telling you where these, this kappa here depends on the arrangement of the electrodes. So here's some examples of some pseudo-sections that we've acquired in the past. If you have gaps or lines in your data, your data probably is quite poor quality. You might have bad coupling. You might not have put the electrodes into the ground. If it's very resistive ground, you may want to use salt water or something to get a good coupling. But these are examples here of excellent data quality. And what we do then is take our pseudo section. Here's another example. This is from the farm just out there, Texas A&M farm. And we have a nice even distribution of data. By a process of tomography, we can reconstruct the Earth resistivity, and we know out there that there's a sand layer overlying a clay at about 6 or 7 meters. So we can get an image Here's our electrodes on the surface. This is our depth. So here we're going down 12 meters, about 30 feet, and we can map the subsurface properties to that level. So basically what an applied geophysicist does is very similar to a radiologist in a way, is that we collect these images which require some kind of interpretation. So we would work with engineers, for example, to basically to try to interpret these results and then correlate our image findings with other tests and use the test results to help design engineering projects, much as a doctor would use a radiologist to conduct a series of tests, choose the appropriate imaging technique, and then provide information about that would direct, in this case, patient care. So we kind of perform an analogous role for the engineers that a radiologist would do for a doctor. And just to show you here, finally, before we look at some case studies, that we can roll our electrode array along. So here's the first setup. And then once you've collected your data for this setup, if you have got a long stretch of highway to image, you can then take sections A and B and move them over here and move your box and your battery over and then keep acquiring. So one example I'll show you from El Paso is that we had 11 of these roll-alongs over a period of 2 days. And we went 800 meters long. So we'll look at some examples now. This is out on FM 696 near Lexington. There was a problem with the road. They were constantly having to put new asphalt down. So we went along the side of the road and made these are our electrodes, several roll-alongs here. I think there were 5. So you can see these are electrodes. And we came up with this image down to, sorry I'm using meters here, but came down to about 75 feet. And what we found was that there was an area of low resistivity in blue, which was indicating electrically conducting materials. And that turned out with some augering that Tom Scullion and those guys did, that turned out to be an area of wet clay. And here is a high resistivity area, which turned out to be fine dry sand. And this area was the area where they were having roadway problems. And more than likely, it was because of water being retained under the road in this clay. So here you can see that here. And basically what you can get with the ERT image is a picture of the body, the actual geometry of the clay body here. And I want to point out that this data, we started work at about 9 o'clock or 10 o'clock in the morning, and by 1 or 2 p.m. we could have this image in the field. We could see it in the field, and then we could then make a decision while we're out there about what it all means. This is another example we did in El Paso. Here's the Mexico wall. And this 275 highway, 375, was underlain by some kind of landfill. And it was causing the roadway problems, like bumpy roadway here. And so this is where we did the 11 roll-alongs. You see each of these are electrodes over 2 days. And we noticed some areas of low resistivity, which probably which indicates some kind of moisture, or in this case, some kind of landfill products under the road. And incidentally, these were the same places that were detected by GPR, ground penetrating radar, also identified these areas as potential problematic areas. So this is the sort of information we would pass along to the roadway engineers. And just a final, before I get to the bridge study, just finally, I want to point out that you can build up these images in quasi three-dimension images. This is again at the Texas A&M farm, and each of these corresponds to an electrode ERT deployment. And in this case, here's the river, and here's the floodplain, and here we can see this sand channel in the alluvial floodplain passing, going a straight, a linear feature, which eventually comes up here and discharges as a spring into the river. So we can map out the subsurface by a three-dimensional, in kind of a quasi three-dimensional way. And I'll show you at the end how we've done this for the bridge example. So as far as mapping electrical resistivity is concerned, we know that it depends, the bulk resistivity of the soil, which we can approximate to first order as a sand-clay mixture, it'll depend on the sand, whether you have sand or clay, with sand being more resistive than clay. I'm plotting here conductivity, electrical conductivity. So clay is more electrically conductive than sand, and it will depend on the salinity of the fluid there, of the water. So if it's fresh water, it's resistive. If it's brackish or saline, it'll be more conductive. And you can see how if you have a sand, the trend of the bulk resistivity of a saturated sand goes like this, and a clay like this. And this is the conductivity of the pure electrolyte. So with clays, you can get more conductive than the saturating fluid. With sand, you can never get more conductive. It's much more resistive and never reaches the level of the electrolyte conductivity, because we're measuring the bulk. We're measuring the bulk resistivity or conductivity of the soil. So this is the example from the bridge. So this bridge here was between near Belleville. Here's Hempstead and Brenham, right here. And we deployed. The engineers asked us to deploy 3 lines here, 1, 2, and 3, and they were building a new bridge here across this creek in Austin County, right here. And so this is the old bridge, and this is the new one. And you can begin to see a problem here is that because of the scour of the foundations for the high discharge sometimes of the creek, is that there was a lot of concrete that engineers had placed in here in order to stabilize the foundations. But when they tried to build new ones, they kept excavating and running into this concrete debris. And so here's the beginning of the construction of the new bridge. Here's the old one. And the concrete debris is under here. And they started the excavation process. And this water-filled area here became water-filled because of the excavation. But there was concrete there. And they were the cost of removing that concrete was rather high. So what they wanted to know was how far did the concrete extend so they could build their new foundations here, or bent, or what have you. So this is another view of the field site. Again, during high discharge, the stream scoured out some of the foundations. So this is one of our lines we deployed here, and this had 56 electrodes. This was fairly easy to put in the ground. At El Paso, it was more difficult, so we used electric drills to get the electrodes in because it was all that caliche stuff. But these were fairly easy. And again, it took just a couple of hours to do this line, or even 1 hour to do this line. We did 3 lines in total. So by 2 p.m., we were finished. So here's an example of some of the concrete rubble underneath the abutment. And these are our lines. These electrodes we had to put into the concrete. So that's where we used our drill to get just a few of the electrodes in. But as you go over here, there's more alluvium, and they were more simple to put in. But you can see some of the challenging conditions working on to do these geophysics problems. And here's another line. This is the line. This is where we were looking at the concrete. They wanted to know whether there was concrete under this area. This is where they wanted to install the foundation. And so this is the line further to the away from the concrete debris. So it was decided to conduct an ERT survey to determine the spatial distribution of the concrete debris. And we know from previous studies that the concrete rubble zones have a resistivity generally in the order of 50 ohm meters, whereas the intact concrete blocks, which don't have the rubble associated, are more resistive, electrically resistive, 300. And we know that compacted clay soils, depending on the water content, are less resistive or more conductive. So we use these kind of numbers as guidelines to tell us what material is in the ground. So this is line 1 here. This was done on this region, away from the concrete rubble. And I think we started here and finished up here. And so making the interpretation, this is our alluvium from the river alluvium. And above we had sand. This was like a sandbar. So you can see the sand here. And this depth is several feet. And then what we're finding here is areas that may be due to some concrete rubble. And it may be even out of the plane of the diagram. But that was, this area here is right here, and looks like it's relatively free of high resistivity blocks. As you'll see in this diagram here, when we come down here, we look at this area here, we got a very large signal at depth, which is more than likely to be the buried concrete they suspected was in this location. You see a really high resistivity block here. And this concrete rubble at the surface, including the ones that electrodes we put in with the hammer drill, is all this red stuff up here, and this is our alluvium, and there may be some more rubble here. You can begin to see the foundation in the tomogram. And then on line 3, right here, this area here, across the water-filled area where they did the excavations, and even up to here, contains this concrete rubble, whereas the start of the line is a lot more clearer, a lot less resistive. So this area looks relatively good from a point of view of placing a foundation, where this area doesn't look good at all because of the massive amount of concrete debris. And again, here we can put these together into this sort of fence diagram with the map underlay. And here's that big concrete block under the bridge that we looked at, under the water-covered area. This is the concrete rubble under the bridge, and some more concrete rubble here. This area here is relatively free of red spot stuff at depth. And so it was decided, actually, the original plan was to put the foundation here, but the engineers, after discussion, moved it over to here, and they were able to change their span lengths in order to accommodate that. It was in this case, we were lucky. It was a fairly simple design change, just to move the foundations from here, where you have a lot of concrete, over to here, where there's not so much. So just sort of to conclude the talk, is that we made 3 ERT transects at the bridge construction site. This site was underlain by concrete rubble. We didn't know the spatial extent of it. The rubble was originally placed to fix a scour hole around the existing bridge foundations from high discharge in the stream. And some of the so when the new bridge was about to be built, some of the rubble was removed by excavation, which caused the formation of that water-filled area. The ERT surveys that we did indicate that there was indeed some additional concrete rubble beneath the water-filled area, perhaps to 30 feet or 10 meters depth, and also to the east, but shallower there. So what we discovered was that the line 1 tomogram was the least affected by the rubble, and from an engineering standpoint, it was determined to be the most suitable place to install the new foundations. While we cannot guarantee that concrete debris is absent because of the lack of the really high resistivity features in the tomograms, we're quite reasonably confident that there's not, at least there's not big concrete blocks there. And then you can read this about the installation of new foundations. Importantly, just to finish, is that the interpretation of these kind of images is somewhat, you may call it subjective, but it does require a certain amount of judicious decision-making because of ambiguities of, as you're probably aware, of geophysical imaging. And this is caused by the fact that many materials have overlapping ranges of electrical resistivity. So sands or dry sand versus concrete is difficult to tell apart, as is like briny sands and clay are difficult to tell apart because both of those in that case have low resistivity. So what we really need to do is to have an idea of what kind of materials are there through boreholes or some other information. When you're working at a construction site where you have construction materials, you have rubble, you have excavated pits, you have foundations in place, it makes it even more difficult to interpret these images, and you have to take some great care to do so. A general rule of thumb is that assigning causative structures, I should say, the assignment of what's causing the signal should always be regarded with a certain amount of caution. But it's an indicator. It's an indicator of subsurface conditions. But I recommend that it, wherever possible, followed up with ground truthing, such as borings and excavations and so forth. I'd like to acknowledge Tom and Darlene, and I think Lee and Jason came out on most of these projects, the TTI engineers. They've been really supportive of this work that we're doing. And hopefully we've been useful to them and to TxDOT for this. And I want to point out that the geophysics it seems to be gaining popularity among geotechnical engineers, and there's a lot of other state departments of transportation that are actively doing this, exploring ERT as an option for their subsurface geotechnical investigations. And so that's pretty well brings to a close my talk. So thank you.